All right, section 4.4, we were talking about something called the definite integral. And we had worked through several pieces of things, all based in large part on this definition. This idea that these integrals from a to b, this is called a definite integral because it has these limits at a and at b, is the equivalent to having a image where we have infinitely many rectangles under a curve, right? And we haven't really sort of delved into how we actually process that. That is in 4.5. But we have gotten to this point right here where we're going to talk about a theorem that we had done last time. Maybe I should have paused briefly the theorem. Let me go back. This theorem, 4.2, had this statement that allowed us that if we had addition or subtraction, it's actually true as well. We had these constant multipliers. We had this ability to sort of separate them into pieces. Okay? That's actually the example that we're going to work on first today. All right, so we actually are given three separate integral values. We're told that the integral from 2 to 4 of x cubed dx is 60. Of simply x from 2 to 4 is 6. And then the integral from 2 to 4 of dx is actually the number 2. So what we've got right here then on problem number, and those actually are correct values too, by the way, and we'll talk about how we find those, excuse me, in 4.5. But we're going to use that theorem on this problem to be able to separate these into pieces and then evaluate it. So what this actually is showing you down here is that how many different pieces can we separate this into? 3. Because we have addition and subtraction separating 3 different pieces. It's a trinomial. So we're actually going to be able to separate this. The 4 will be on the outside from 2 to 4 of the function x cubed dx. Remember, anytime you have the integral, you have the dx. They go together. The next thing is you actually keep the sign. So this is a subtraction sign from 2 to 4. The function is x dx. You can write it like this, or if you'd like to understand that this is actually like a -1 in front of the x, you can put a 1 out here, if that helps you to sort of process it a little bit better. It doesn't really matter, but it's another way of thinking about it. And then I have a -7 and an integral from the 2 to 4 of just dx. And again, if you want to think about this 7 coming out, you could put a 1 right here. But I kind of like it written as the dx because that actually mirrors exactly what's written up here. So the way that this is actually set forth then, all 3 of these pieces are exactly these pieces up here, right? So we can use the right-hand side of what each of those pieces are in place of what we have. So we have down here 4, and the integral from 2 to 4 of x cubed dx, well, that's 60. Minus the integral from 2 to 4 of x dx, well, that's 6. Minus the 7. And then the integral from 2 to 4 of just dx is 2. So 7 times 2. So it's just a substitution. You're just identifying the pieces and you're substituting them into the formula. Okay? What's that work out to be? 220. And that's all she wrote on that one. What do you think? It's not bad, right? It's not bad. All right, one last example in this section talks about using geometric formulas, and I promise they're not going to be complicated formulas. They're formulas that you know and you keep using over again. We're going to use formulas to actually approximate this. So in order to do that, we need a picture to figure out what kind of a formula we need to use. So either grab a calculator or you can graph this one pretty easily by hand. This is an equation of 3x plus 4. What is that an equation of? It is a line with slope 3 and a y-intercept of 4. So we can start over here with a y-intercept of 4. So when x is equal to 0, because it says I'm supposed to go from 0 to 2, my y value is 4. When x is equal to 2, what's my y value? Just plug the number 2 in. What do you get? Plug the number 2 into 3x plus 4. 10. Thank you. So this is 10. So this is going to go from 2 to 10, and it's a line like you guys said, so it looks something like that. And I mean, it's a line that goes further than that. It's just that the only portion of the graph that I care about is the graph between 0 and 2. Because what I'm actually asked to do is I'm actually asked to find the area. That's what this notation means. Find the area between x equals 0 and x equals 2, trapped between the x-axis and this line in this case. So this is the area I'm looking at. It's not shaded fully, but you get the idea. There's at least 2 different ways you could do this problem. One way is to simply recognize what this shape actually is. Do you recognize what this shape actually is? It's a trapezoid. Very good. And then if you're going to use a trapezoid perspective, you'd have to know the area of a trapezoid. That's the part where you may or may not remember it. That's not sort of one we use all the time. But it's not a bad one to remember. It's not terribly difficult. What is the area of a trapezoid?
1/2 B1 or B1 plus B2.
Okay, so we have a 1/2 in there. We have a B1 plus B2. Those are the two bases. And then we have a height, right? They're all multiplied together. And there's different versions of how you can sort of write this, but it's got all these three pieces in it. All right, so this is one way to do it, to recognize you have a trapezoid. Now, in the problem, you want to remember what the base is. And so this is sort of a trapezoid. It is a trapezoid, but it almost is sort of on its side from the ones that you're used to seeing. The bases are the two parallel sides. So the sides that are actually parallel are my vertical sides on this one. So this side and this side. So I don't care which one you call B1 and which one you call B2, but one of them's B1, the other one's B2. So then the height is actually the base length along the x-axis of what I have. So if I go with this sort of a picture and I use this particular formula, I have 1/2. What's my base 1? 4. What's my base 2? 10. And what's my height? 2. So multiply all that out, what do you get? 14. Did anybody see something different when they looked at this than a trapezoid?
It's also a triangle and a rectangle.
That's exactly right. You could recognize that if you split this, it's not in half, but into two pieces, that you have a rectangle down here and you have a triangle up here. And the nice thing about thinking about that perspective is that you don't always remember the area of a trapezoid formula. It's not just one we use all the time. I mean, like you're going to remember it now for the next 2 weeks, but after that you might not ever remember it again. So as a general rule of thumb, when you're working with a shape that you don't know how to deal with or you don't remember a formula for, splitting it into things that you can deal with is a really good way to think about it. And this is a good one because you know the area of a rectangle and you know the area formula for a triangle. So let's start with the rectangle down here. So we could think of this as the area of a rectangle plus the area of a triangle. So if we do the area of the rectangle, how do I find the area of a rectangle? Length times width. And so the length here would be, give me one of them, 2, and then the width would be 4, or vice versa, right? It's 2 and 4. Area of a triangle is 1/2 base times height. So, and again, I don't really care which one you call the base or which one you call the height, but one of them is this green sort of piece that I've drawn in, and this has length 2, yeah. And then the other one is this piece right here that's a portion of what we labeled B2. How long is this piece right here? That's 6. And of course, this ends up being, this is 8 plus 6, which ends up being the same 14. Thought about from a different perspective. There's one example in your homework that uses something where you can use triangles and rectangles or trapezoids, things like that. There's another example that requires that you remember the area of a circle. What's the area of a circle? R squared, okay? It's not going to be the whole circle, so be aware of that, but it's going to require that you remember that formula. That's it. Is that right? Okay.